Morandotti, University of Torino, and Marco's research evolves around calculus of variations, applied calculus of variations, and today we will speak about semi-discrete modeling, disclinations, and dislocations.
Thank you very much, Martin, for the invitation, and thank you all for being here today, both in presence and from home. It's actually my first scientific visit here in Prague, although I visited the city many years ago, and it was good to be back to see how it's changed. So today's seminar is going to be about a variational modeling for disclinations, essentially, and then we will see how they are related with dislocations. And first of all, let me acknowledge my two co-authors in this journey, who are Pierluigi Cesano from Kyushu University and Lucia De Luca, who is currently at the CNR in Rome, at the National Research Council. So the menu for the afternoon is going to be the following one. So I would like to tell you briefly the definition of dislocation and disclination, as they are intended to be measures of defects in a material, usually crystalline solids. And then I would like to frame things in a variational setting, meaning that we would like to define an energy, and we would like to find minimizers of this energy. And in the variational perspective, this allows us to find equilibrium configurations of a material subject to the presence of defects. And the fact that there are defects is tracked by something which is called the kinematic incompatibility. So I will tell you a couple of things about kinematic compatibility, which dates back to the second half of the 18th century. The 1800s, sorry, and then we will see how it can be phrased in a more modern language in terms of some operators, differential operators that are usually those involved in continuum mechanics. And then I would like to start describing a system with finitely many disclinations that are isolated, so they are suitably far apart from one another in a way that they sort of don't interact or don't get too close. And for this, we will write down energetics. And then after this, I would focus on one specific case, which is a dipole of disclination. So in that case, they are very close to one another. And then the dipole collapses. So there will be disclinations with opposite signs, and they will behave like charged particles, like, say, electric charges. And we will see how this has to do with Eshelby's construction. That's something that Eshelby proposed in the 60s. And okay, I wanted this. And in a way, he says, or he proves in the physicist's way, that a dipole of disclinations is equivalent to one edge dislocation. So this brings us back to the beginning of the talk and the title, where I was talking about dislocations and disclinations. And we see the an energetic behavior of this dipole, and we show that in the limit as the length of the dipole vanishes, then we recover the description of edge dislocations that was already studied in the literature. In particular, we recover the expression of the renormalized energy as was obtained by Cermelli and Leoni in a celebrated paper dating back to 2005, and we get all orders of this energy. So let us see what dislocations and disclinations are. So first of all, I would like to focus on the edge dislocations that are defects where there's a failure of closure in the linear part of the deformation, so in the gradient. And these are identified by a line, usually where the defect is. And edge dislocations are identified by the fact that the measure of the defect, which is usually called the Burgers factor, is perpendicular to the line. Whereas disclinations are defects entailing a violation of the rotation part of the deformation. And those are usually say called the wedge disclination. So Volterra in a very long and celebrated paper dating back to 1907 did something that I think in German would be called a Gedanken experiment. So he didn't have anything at hand, nothing that he could touch, no solid materials, but he thought about taking a hollow cylinder. So there's a cylinder with a hole, cutting along one of the sides, and then gluing parts back together. So he originated, or at least what he thought was to create three different types of defects. If he slided the two lips of the fracture in a way, in three different ways. So you could do something like this, you could do the opening thing, and you could do the anti-plane things. And the first two already give origin to edge dislocations, and the other one it would be a screw dislocation, where the defect is like going up on a circular staircase, basically. And he did the same thing by violating rotation. So the idea is that you cut your cylinder in some way, and then instead of moving it with a typical 3/4 of the fracture, you move it in this way. Either you overlap two parts, or you open them wide, but in an angular fashion. And then you can generate positive or negative defects in this way. So if you want me to stick to the stereotypical Italian, I think about pizza. So take a pizza, cut out one slice, and then subtract it from your material, and then force the material to glue back together. So if the material is allowed to pop out in the third dimension, then you form like a little head, and there is not much elastic energy stored in it. But if you force your material to stay in the plane, and this also is not just a matter of modeling, but graphene behaves like this, and graphene can be cut in very, very thin layers, thin sheets, then you store elastic energy in a way. The other way, and this is generally called a positive disclination. If you do the opposite part, so you take the pizza that your friend took out, the slice that your friend took out, and then you stick it in another pizza, then you're kind of opening it in a way, and you force it to have more material inside, and this is this configuration here. There would be like a 5-fold defect and a 7-fold defect, counting the sides of your original hexagon after subtracting or adding the extra material. And so at the center of this pizza, if you want, which in my way of seeing is basically the cross section of a cylinder in which I put plane strain elasticity, then I have a defect. All right. So, and the circuit that was mentioned in the definition here given by Navarro in his book is this one is a circuit that moves around the defect at the center of the defect. And if the material is sound, then you check the undeformed configuration and the deformed configuration, and you go back and close it. If your material has a defect at the center, then your circuit is either short or long by ideally one lattice spacing or something like that. And so as I said, we assume cylindrical symmetry, and we work in the plane strain elasticity assumption. So all the formation is going to be described by a displacement U, which is a field, and sorry, which is not a field. It's something that takes values from a subset over 2 into R. It just describes the motion in the third direction. And then no, it is, sorry, I got confused by the notation. It is a field here. It goes into R2. Okay, so then we take the elastic strain, which is the symmetrized gradient of the function U, and then we associate with it the stress. As it's typical to do in elasticity, we have the elasticity tensor here, which it can be represented by the Lamé constants in this way. And the easiest elastic energy which is stored in the material is this one, is basically just the dot product between the contraction between sigma and epsilon, and it assumes that form. And it can be written both in terms of U, sigma, epsilon, according to the way you prefer to see it. But for us, it will be interesting to see it as a variable, as a functional of the variable sigma, which takes this form here. And this is useful because in two-dimensional domains, one can try and find the Airy potential, so the Airy stress function, which is also something very common in the engineering literature, because it provides automatically the fact that the equilibrium configuration divergence of sigma equal to 0 is automatically satisfied, right? So you don't have to worry about that equation anymore, and you just think about solving the other ones. So the Airy potential is a function B, which enjoys these properties. So basically, it's derivatives, it's second-order derivatives with a suitable placement are the components of sigma. Okay, so sigma, the component 1 of sigma is the double derivative, the derivative over the 2 with respect to y twice of B, and then you've got the switch with the other one, whereas the mixed components are the off-diagonal elements of the sigma tensor with a minus sign. And because of this structure, actually, you can really say that the divergence of sigma is equal is equal to 0. So now if we write the energy in terms of V, we obtain a functional here, G of V, which reads in this way. And it's pretty interesting the fact that the norm square of sigma is the norm square of the Hessian of V, of course, and the trace of sigma is nothing but the Laplacian of V. So this basically makes two nice quantities about V appear here. And if you want to write the Euler-Lagrange equation of this functional, something interesting will come out. And all of this should be subject to the constraint of compatibility if your material is sound, which can be written as the double curl of epsilon being equal to 0. So you might notice a different capitalization, small curl first and big curl later. We use this notation in our paper because of the dimensions. Ideally, everything should be capitalized and epsilon is a 3x3 matrix. But then if you only have a 2x2 one, you need to complete it to a 3x3 and then take the suitable components. In this case, though, this is just one scalar equation, okay? Because of the fact that we work into dimensions, this one is one scalar equation instead of being a matrix equation. And the original relationship that encodes compatibility, kinematic compatibility with this double curl operation dates back to Saint-Venant, and it's called the Saint-Venant compatibility condition. And what we want to do is insert the effect. So now the incompatibility will be measured by the fact that this double curl is non-zero, and it will encode the presence of the defects in some sense, all right? And so just to take a look a little bit closer to the compatibility constraint, we notice this. So if we are in a classical setting, no variational for the moment, so no weak objects, but just continuous and 3 times differentiable with continuity, we have all this information, right? So if we take a function which is C3 of omega with values in R2, then the curl of its gradient is equal to 0. So then the gradient can be split into the two parts, the symmetric part, which is epsilon, as we said before, and the skew symmetric part, which we call beta. And then beta is representable by an antisymmetric matrix, which in 2 dimensions is only identified by one parameter, the element of the diagonal. And this needs to be a C2 function. And then the compatibility condition then can be written in the following way. So the curl of epsilon is equal to minus the gradient of f, if you just compute what is there. And applying the curl operator again gives us the Saint-Venant compatibility condition. So the curl of a gradient is always equal to 0, so the double curl of epsilon must be equal to 0, okay? And then the importance of Saint-Venant work was to prove the opposite implication. So if we have something whose double curl is equal to 0, then that epsilon matrix is the symmetric part of a function U of class C3, so of the regularity that we're interested in. Because all in all, we're taking 3 derivatives here, 1 to create the epsilon and 2 by taking the curls. And this principle can also be translated and is proved to hold in a weaker setting, in a variational setting. So this can be found in papers by Ciele and Ciele, or even in a paper by Jemonet and Krasutsky, where they prove that in this setting, the double curl of this matrix valued field epsilon is equal to 0 if and only if there is an H1 field whose symmetric gradient is precisely the epsilon that we are considering. And because rigid motions are in the kernel of the symmetric gradient, then this field is uniquely determined up to a rigid motion. Okay, so uniqueness up to a point, but rigid motions are fine because physics is invariant by rigid motion. So if we write this again in the following way, we were talking about the curl of beta before, and the 3 conditions that I wrote before are like this. So if everything is fine, if the material is sound, these are the compatibility conditions. But if we assume that there is, so physicists would say, if beta is not a gradient, so if this position here, beta equals the gradient of U fails, then it's not true anymore that its curl is equal to 0. So its curl must be equal to something, which we require to hold in the sense of distribution. And this alpha in principle is a distribution. And then the fact that the beta was not nabla U anymore, propagates through the other conditions in the following way. So you trace the color and you see where it propagates. And then you can also have failures if this nabla F is not really a gradient, but it's something different. So if we do this, then it must be equal to some element in H minus 1, and then this propagates to the double curl in the following way. So for us, actually, the alpha and theta that we're going to consider will only be Dirac deltas, and they are that are supported where the defects are. So alpha is going to be the measure of dislocations, so the first type of defects that I described, and then the theta is going to be the measure of disclinations, the presence of disclinations. And we require them to be Dirac deltas because these defects appear isolated in the material to start with. Okay, so the counting is done in this way. So we will have capital K disclinations and capital J dislocations. This is not important at the moment. What is important for me and what was important for us to recover to create our result was that whereas the measure of dislocations of disclination, sorry, the red one, the theta appears as it is, so as a sum of deltas. If we have the deltas, then the measure of these dislocations appears through a directional derivative in a way, which has to be understood in the distributional setting. Still, there's a derivation relationship between dislocations and disclinations for them to contribute to the curve, to the incompatibility operator. So as I said before, the measure of dislocations, of the entity of a dislocation is called the Burgers vector that counts, say, in which direction there is a lattice mismatch. Typically, it's order of one lattice spacing, whereas the measure of the seven-fold or five-fold disclinations that you saw before in the picture is called the Frank angle, and it's just a number. Okay, so those typical ones would have been pi over 3 or minus pi over 3. So I insisted before to mention the Airy stress function because it is easy for us to convert to the Airy world, to translate everything into the Airy world and see what comes out. So how the equilibrium configuration translates, basically it doesn't translate because the Airy stress function is built for the equilibrium configuration not to appear, the equilibrium equation, that's the black one in the middle, not to appear. But then we still have to deal with the incompatibility condition, which now is this one, and with the boundary conditions. And we assume, say, traction-free boundary conditions. And these are translated in the following way. So it's just a simple computation that if the V is the Airy potential of the sigma that we had before, then curl epsilon equals 0 translates into, up to a constant, the bilaplacian of V to be equal to 0, or in any way, the curl operator translates into the bilaplacian. So basically, sound materials and compatible elasticity corresponds to Airy potentials that are biharmonic. And if they're not biharmonic, we have this forcing term here, which is given in terms of the measure theta. And the boundary condition, the traction-free boundary condition, translates into this one. So the Hessian applied to the tangent vector must vanish. And T is the tangent to the boundary, which we can speak about in a unique way because our domain would be two-dimensional, right? So the boundary is a curve in the plane, and we may assume that it's regular enough to have a tangent defined everywhere. And so we can prove a proposition that these two problems are equivalent. So basically, if one wants to find the equilibrium configuration in the physical world or in the Airy potential world, then they would obtain the same answer. So once the conversion is. And the trick to do this is to decompose the both objects, so either both the epsilon and the V into what we call the plastic and elastic contribution. So the plastic contribution will be the one that encodes the presence of the defects that arises only if the defects are present, whereas the elastic contribution is the one which is compatible. So curl of epsilon elastic will be 0, and in the same way, the bilaplacian of V elastic, of the corresponding V elastic, will vanish. Okay, and to do so, we do this, and we obtain some functions. These can be computed by hands in a way that are of this type. So consider this V bar. This V bar is a biharmonic function, and it can be translated vertically, say, to impose the boundary condition that you want. So maybe this one has zero boundary condition or whatever. Then you can adjust it to have zero boundary condition at the boundary of a disk. And this is basically the source of a disclination centered at the center of the disk. And then we may translate them. So we do this operation here. Instead of x, we put x minus yk for each of the k's, and then we pre-multiply by the Frank angle. And this vk is the one that encodes the presence of a disclination with Frank angle sk in position yk in our material. And the other thing that was a crucial instrument for this equivalence result to be proved is the fact that we have this geometric this lemma, which is geometric in nature, that tells us that the tangential, so the action of the Hessian on the tangent vector on the boundary of a set, so on the boundary of a set is zero if and only if v is and its normal derivative are the trace of an affine function on the boundary. Okay, because so ideally uniqueness will be established up to affine functions in the real world, because these are those that happen to be in the kernel of the gradient of the Hessian operator. Okay, and then we don't have to worry about the equation, the harmonic equation, actually, because in that case we have 4 derivatives to take. So they will also be, say, in the kernel of the harmonic operator. And when we're dealing with a system of finitely many isolated disclination, that's the full theta measure that I introduced before. So this curly WD stands for wedge disclinations. Then we came up with this functional I, which encodes the G functional that I introduced in the second or third slide. So this one is the elastic energy written in terms of the area stress function. And then we added this term, which is the, say, if theta is a measure, this needs to be understood in the sense of duality between measures and function. And we take this duality between the measure theta and the function v that describes, that's the area potential, okay? And as I said before, minimizing I theta in this overall H2 functions that are such that the Hessian applied to the tangent vanishes at the boundary is equivalent to minimizing those that are in H2 zero, because we can subtract off an affine function. So we choose our favorite one, and we take the zero function. Sorry. And so now we started studying what happens in a disk, for instance. So that was the easiest configuration to look at. So we take a disk, and this could have been located at the origin, but it's just to keep track of where the center plays a role. And we can claim that this function VR, which is suitably defined by rescaling the V bar that I introduced before, so the one that was mod squared of x log of mod x, and in this case it would be mod square of x minus xi log of mod x minus xi, is the function that solves the Laplacian equation. Okay, so the rescaling factor also involves the physical quantities, the Poisson, the Young modulus, and the Poisson ratio, capital E and nu here. But so this one is the one that gives, say, the one disclination at the center of the disk with Frank angle S. Okay, and it is also such that at the boundary of the ball it behaves nicely with respect to the boundary conditions. It's a matter of a computation. It can be done very, very easily. What's interesting though is that when you compute the energy, you obtain these results. So the elastic energy scales like r squared if r is the size of the disk. Okay, whereas the duality with the delta gives the same contribution but half. Actually, no, sorry, twice as much. Okay, so twice as much. And so we can compute explicitly the minimizer for this case, and it's going to be given by this quantity here, which has 2 particular features. It depends on the Frank angle with the square of it, which is fine because we wouldn't really care if it's a positive or negative disclination. The stored elastic energy measures the presence of the defect, and we're happy with that. But it also scales with the square of the radius of the sample. Okay, so if you're looking at some defective material, which is a disk, and then you've got a disclination in the center, then it scales in this way there. So this energy, contrary to the one of the dislocations, is not singular in the center of the dislocation, because when R goes to zero, this energy goes nicely to zero and nothing happens. The bad thing about this energy, that scales quadratically with the size of the sample. So if your sample is very, very large, then the energy grows very, very much. Okay, so the whole idea of studying energies for dislocations and disclinations, defects in general, because of the fact that they are associated with fields not being regular, are expected to explode when you take, say, the elastic energy of them, when you take an L2 norm of some sort. All right, so the whole production in identifying the importance or the magnitude of dislocation or disclination must be done in a way that we rescale the energy, we renormalize it in a way to identify, so to clean it from the part that we know explodes to infinity in the way we know it explodes to infinity, and then to see what's left. And then precisely that part will be what allows us to identify the energetic contribution of the defects. And I will come to that later when we do some rescaling. But then the rescalings are done when we make the interplay of one positive and one negative disclinations next to one another, which means we're considering dipoles. Okay, so in this context, then we want to consider a positive and the negative disclinations placed h far apart from one another, and we take them on the x-axis. And then this construction done by Eshelby says that in the limit as the dipole length goes to zero, we recover a defect which is an edge dislocation, whose Burger's modulus is precisely the Burger. So sorry, whose Burger's modulus, which is the modulus of the Burger's vector, is precisely the Frank angle. And the idea is like this: so you take your pie or pizza or disk, whatever, and then you place these two defects h far apart in this fashion. So and then you make these two cuts, and then you slide the slice a little bit off to the left. And then when you're in this configuration, you glue the two things together. So the two lips that are separated up here must be glued together. And then in the limit when h tends to zero, say the vector that identifies the joining between these two lines, which in our case will point, in this picture will point somewhere along the, like in the direction of the first quadrant, will sort of become vertical. So if the original dipole was oriented as E1, then the Burger's vector will be oriented like E2 in this way there, when we take the limit as h goes to zero. I must say that Eshelby's construction is very easy to read, but then there's a kind of a trick where there are two quantities that should go to zero together, and he's a little bit sloppy in my opinion about that, but I mean, for the purpose of the computation, he gets his result. So it was our purpose to try and fix it correctly. And the idea is the following one. So if we have a dipole, then we have a measure, a wedge disclination density, which is this theta h, which is a delta centered at h with sign plus, and a delta centered at minus h with the sign minus, right? And then, since this equation is linear, then we can say that if we add the effect of the two solutions, then that function b h bar solves the Laplacian equation equal to minus this theta h for the one that we've constructed, all right? And now the question is, how does this behave in energy? So what's the energy scaling of this, involving the fact that there is a length h appearing? So we can compute the following thing. So we take a ring like an annulus between radii small r and big R, and then we can evaluate the h2 norm of the function the h bar in this annulus here, and we discover that it scales like constant times h squared. All right, so if we divide and renormalize by the square of this dipole length, we get a finite quantity. And moreover, if we rescale the full elastic, the whole elastic energy by h squared log h in a way, which is, so h squared reminds us of the fact that the energy scales like the square, and then the logarithm reminds me of the fact that the dislocations scale like the logarithm of a little core centered at the dislocation. Then this one is a finite number. Okay, so then this suggests that the h squared log h with a minus sign, I mean, it's just like this, is the right scaling that at which we should see some physics happening. And moreover, we can prove also this result. So it's still about scaling. And if we consider the space H20 and look for minimizers of this energy here, the one with the dipole of disclinations in the ball of radius R, then the correct scaling of the elastic energy is h squared log h, and it gives us this contribution. And then if we also add the disclination contribution, that was the theta against the v, we get this contribution here. Okay, so again, the linear part, the theta against the function, the duality is twice as much as the elastic energy with the opposite sign. Okay, so there's a positive sign here and there's a negative sign there. And the way we treat the limit in h going to 0 is by a core radius approach, which is the winning strategy for dealing with dislocations usually. Okay, so what they do with dislocation, what it is usually done with dislocations, you fix a dislocation and then you look at a small core of radius epsilon around it, and all the energy is concentrated in this core, and the energy scales like the log of the radius of this epsilon size, right? Which is the thing that we would like to throw away because we know it behaves and makes the energy explode, and then we see at lower orbit terms. So how do we get to that? So we do this. So we look at the fact that the rescaled function, or like measure theta h over h, converges to the derivative of the delta in the x1 direction formally, right? Because the you see it here. This one looks very much like the approximation of the derivative, okay? Because you put a delta at h, a delta at minus h over 2, and then you divide by h, and then it's like taking the derivative with respect to the x1 direction, e1 direction. And so we expect that the solution, if we scale, so the dh over h, will formally converge to a solution of the bilaplacian with this as a datum to the right-hand side. Okay, and this one indeed is so the corresponding V is the area potential of a stress function that corresponds to an edge dislocation whose Berger's vector is B, oriented as E2, and its magnitude is going to be the Frank angle as that was given for the disclinations, right? Okay. So as I said, if we apply the theta h to a w to a function, we obtain this thing here, okay? And then if we rescale this by dividing by h, we would like to see something by h squared. Sorry, we would like to see something that is like an incremental quotient. Okay, so the wh can be rescaled as h times another function w. And we know that the elastic energy scales quadratically because it was the square of the gradient, the Hessian, and the square of the Laplacian. So an h comes out with power 2. So we divide by h with power 2. And here we identify this incremental quotient of the w. All right. So in this, we expect this to converge to the x1 derivative of the function w. And this is actually what we can prove. Okay, so it goes through a bunch of lemmas and rescaling and renaming of the functions, but I don't want to be too precise here because results are technical. I just want to give you the flavor. So basically, we can prove that if we take a minimizer of this rescaled energy, where the h is still strictly positive, so the dipole is still there, and we look at it in a core of radius epsilon, which is bigger than h. So starting from some multiples of h to maybe different orders than h, it doesn't matter, it needs to be just larger. Then we have the minimizers that are unique because we can prove that they are unique, converge strongly in h2 to the minimizer of the function, of the functional corresponding to the fact that h has collapsed to 0. And then we can compute the energy explicitly. And this one enjoys the presence of a terms log of R over epsilon. So R is the size of the sample, epsilon is the size of the core, and this is precisely the same energetic behavior that dislocations have. And now if we have dislocations, on the contrary, we can approximate them by dipoles of disclinations, constructing them with some sort of reverse engineering process, right? So dislocations will be placed randomly in the material, and they will have their own Burgers vector. So by the fact that the dipole needs to be the rotational by pi over 2 of that Burgers vector, we can construct dipoles which will converge if this dipole length is converging to 0 to that dislocation that is given to us through the measure alpha here. Okay, so we construct the corresponding theta h in this way, and this is precisely the same the procedure that I told you. And then we have that the unique minimizer of the energy corresponding to the theta h will converge the unique minimizer of the energy corresponding to the measure of these dislocations in the punctured domain, right? So we take omega epsilon. Actually, it's not a punctured domain. It's kind of a Swiss cheese type of domain. So omega epsilon alpha is omega minus disks of radius epsilon centered at each of the points of the support of the measure alpha. And these disks must be taken in such a way that they do not overlap and they do not overlap with the boundary. If the dislocations are far apart, this is possible to do so. So it's all fine. And now 2 words about the limits, and then yeah, I think I will be quite on time to conclude. So what we did was to study the limit now as epsilon goes to 0 of this functional that we have obtained, and we recovered the result in this paper that I mentioned at the beginning by Cermelli and Leoni. And in order to do this, we need to bring to the limit as epsilon goes to 0 the minimizers that we found before. So again, we divided into 2 parts, the plastic part and the elastic part. And in a way, the plastic part is the one that comes from the presence of the defect, which, as I showed you before, can be written explicitly. And the elastic part, W tilde, the small W tilde here is an unknown, and it would come out of a minimization process. And so basically, the point is that minimizing the functional over this full displacement W, well, displacement, say, in the area world W here, is the same thing as after this decomposition, is the same thing as minimizing the functional with the tilde, which is the one that only involves the elastic part. And this functional is determined by the elastic contribution of W tilde. Then there is an interaction term between the disclinations and the W tilde. And then there is something which comes from the, say, the theta or the delta applied to the W tilde here. Okay, so this scalar product here between the rotated Burgers vector and the gradient of W. And we proved that if epsilon is small enough, so in the limit as epsilon goes to 0, the minimum problem has a unique solution. And this one cannot be characterized explicitly, but it can be characterized in terms of the problem that it solves. So it solves this problem here, this PDE here, in the sense of distributions. And that's the PDE that we expect. Okay, so if you remember one of the first slides, I had that the incompatibility, which now is the bilaplacian operator, was something having to do with directional derivatives of the delta, and this was for the part concerning dislocations. Okay, and this convergence here is. So we only can say that the W epsilon alpha, which is the minimizer of the functional there, converges to W alpha 0. So when the core has shrunk to 0, strongly in the compacts of omega punctured. So we take away the points. We need to stay a little bit far away from the cores, otherwise there is this logarithmic explosion. And that's precisely the same limit that Cermelli and Leoni had. All right. So for them it was H1 log because they didn't have 2 orders of derivations, but it's exactly the same thing. And the strategy of the proof is again to split this into elastic and plastic contribution, and then use convergences that are proved in this way. So the first one is that we can squeeze the functional for the W tilde, so the one for the elastic part, in between these two controls from above and below in terms of the H2 norms, the H2 norm square and the H2 norm with power 1. And this is possible to do with constants that do not depend on epsilon. All right, so this amounts to proving a slightly non-trivial epsilon independent Poincare inequality, right? Because if you apply Poincare inequality blindly, then you will get something that depends on the size of the domain, but it can be improved in a way that it does not depend on the size of the domain. And then the other proposition is this one that we managed to prove this explicit expression of the energy, right? Which involves again the elastic contribution of the W tilde as we expect, something and a bunch of terms that involve the interaction between the presence of the dislocations and these elastic functions. So the capital W's are those coming from the dislocations, and they interact in a non-trivial way with the elastic part. Okay, then we can prove that the elastic part is biharmonic, so it really corresponds to something which is compatible in the physical world, and the minimizers, the minimal energy converges to the minimum of the energy as epsilon goes to 0, which is the last statement there. And the expansion that we can prove is the following one. So the full energy can be written as the summation of these terms. So something divergent with log epsilon, which is what we expect because dislocations have a log epsilon diverging energy. Then there are the last two terms. So omega epsilon is something infinitesimal with epsilon, and f is something of order 1 that depends on where the dislocations are placed. And then there is this f alpha, which is the most important part. This is called the renormalized energy. And it's an energy that kind of forgets about the mechanics in a way, because it doesn't depend on the deformation fields. It only depends on where the defects are placed in the body, right? So we make it depend on alpha. It depends precisely on the points where alpha is supported, and it can be split in turn into 3 parts. One which is called the self energy. So dislocations create or store elastic energy just because they are there. Then there is an interaction energy between one dislocation and another one. So it's a pairwise interaction where they all come into play. And it's got kind of a bad expression. It's kind of elaborate, but it's the one down here. And then there is some purely elastic energy, which is the functional tilde of the W tilde that was written there. Okay. And this has an agreement with precisely with the results taken by the paper of Ciamellioni at all terms, so we can identify singularly and individually all of these terms. And so with this, I would like to thank you for your attention.